Hi everybody, and welcome to the beginning of chapter 13. We are looking at page 18 in the workbook, and this chapter is about vectors, a very important tool that we'll be using a lot throughout the semester. Okay, so this section we're going to be just talking about the basic definition of vectors, some of the things we can do with them, and what they really are. Let's start off with this definition. Okay, so a vector is a quantity that has both a magnitude and a direction. You probably know some examples of vectors already. And there's kind of a nice way to graphically represent vectors. We're going to represent those as arrows and talk about just some of the notation that we can use. Right? So if we glance together at the preliminary example down here, they give us a graphical representation of some vectors as arrows, and we want to just do a little bit of work with those, talk about the various notational ways that we could write those down. So let's make some observations here. Okay, so take, for example, the vector p, okay, that we're looking at here. We can write that vector down in what's known as component notation. And what we want to focus on is the starting and the ending point of the vector. Okay, so we're starting at the origin, and to get from the beginning of the vector to the end, notice that we have to move 5 units to the left and 2 units down. The way that we can represent that notationally is to write negative 5i minus 2j. The I and the j are just indications of directions that we need to move, or distances that we need to move in the x and the y direction. So negative 5 along the x-axis and negative 2 along the y-axis. Okay, what about q? How would we represent that in component notation? Well, there, if we start at the beginning, we need to move 3 to the right and 3 down, so that's going to be 3i minus 3j in ij notation. Okay, and you kind of get the idea here. Let's see, what about v? Okay, well there, we need to go 2 to the right and 3 up, so that's going to be 2i plus 3j. And what about w? Okay, well notice that w points in exactly the same direction as v and has the same length, and so its description is exactly the same as v's. We need to go 2 to the right and 3 up, so actually 2i plus 3j is also w. That may seem weird because these two vectors look different on the piece of paper, but as vectors they're actually equal because of the fact that they have the same length and direction. It doesn't matter that they start at a different point. All that matters is that they have the same length and direction. Okay, and this is getting a little cluttered here, so I'm going to go ahead and just erase some of the markings that we made. Okay, let's talk a little bit about operations that we can do with vectors. So for example, we could take a vector and multiply it by a number. Okay, that 2 that we multiplied by, we use the term scalar to represent a number, okay, just a constant. So we're going to multiply by the scalar 2. And so 2 times v would just be taking 2 and multiplying it by the vector, the component representation that we had for v. If you do that and just multiply your components by 2's, you're going to get 4i plus 6j. Now what would the vector 2v look like? Okay, let's pick a starting point. It doesn't matter where, so I'm just going to pick that point. And if we draw 4i plus 6j, we're going to go 4 to the right and 6 up. Okay, and there would be our vector 2v. Do you see any relationship between v and 2v? Okay, notice that 2v points in the same direction that v does, and it's twice as long. So the 2 just had the effect of magnifying the length of v. Okay, what about negative v? Okay, well, same idea. We just take a negative sign and just kind of negate those 2 coordinates. So we're going to wind up with negative 2i minus 3j. How would that vector look? Okay, well, let's pick a starting point. And so if we go negative 2i minus 3j, that's going to take us down here. Whoops, that's just negative v, sorry. And how is that vector negative v related to v? Okay, notice that all we did is we reversed the direction, so it has the same length as the vector v, but it's pointing in the exact opposite direction. That's the effect of a minus sign. Okay, and one other thing that we're going to want to do with vectors is to be able to find out their length. There's a special notation for that, double bar. Sometimes that's called a norm. I'll use the term length sometimes, and I'll use the term norm sometimes. That's just a word for the length. And finding the length of a vector is just finding a distance. So we can use the distance formula to do that. So the components of p, going back up here, are -5 and -2. So to find the length, we're just going to take the square root of the sum of the squares of those components. Okay, if you do the arithmetic there, you're going to get the square root of 29, and that's just the length. Or magnitude of p. Okay, let's do that for one more of our vectors. What would the length of q be? Okay, well, same idea. Formula for q is sitting up here, so we'll just take the square root of the sum of the squares. Okay, and this time we're going to get, let's see, the square root of 9 plus 9 is 18. You could leave it like that if you wanted to, or if you want to get fancy and simplify that a little bit, that's also the 3 times the square root of 2. Okay, either of those would be okay. Okay, so there's kind of a brief tour of some vector operations and finding the lengths of vectors. Let's move on to example B here. This is a little bit more work. Okay, it turns out that there's kind of a nice conceptual graphical way of thinking of vector addition. So in this example, we're going to start with two vectors A and B, and I'd like to start this problem by graphing those. And let's make the origin our starting point for both of those vectors. We wouldn't have to do that, but we'll do it because it's convenient. So 2i plus 3j is going to be 2 to the right and 3 up, so that's going to look like this. Okay, there's A. And then B, 4i plus j, that's going to be 4 to the right and 1 up. Okay, so that's going to look like this. And what would the vector A plus B look like? Well, let's do that calculation below here. So if we take the components and just add those, okay, 2i plus 3j and 4i plus j, we're going to get 2i plus 4i is 6i. Just combine those coordinates together, and then 3j plus 1j is 4j. Okay, let's plot that vector. Okay, so that's going to be 6 to the right and 4 up. So 1, 2, 3, 4, 5, 6, and 4 up is going to put us there. Okay, so A plus B is that vector right there. Okay, well that's nice, but I kind of promised you a nice geometric interpretation here. Okay, and so what I'd like you to notice about this diagram is the following. So the vector B that you see at the bottom, there's a copy of B kind of sitting here. Notice that that vector has the same I and j components. It's 4 to the right and 1 up. Okay, and then there's another copy of A sitting here. And so what's interesting about A plus B is that it forms the diagonal of a parallelogram, okay, that we just drew. Okay, and that's a property that the sum of two vectors is always going to have. And I want to just make one other observation that's going to be useful. Okay, so you can think of A plus B as kind of being the combined action of A and B. So imagine that you start at the origin, okay, and you want to talk about the vector A plus B. Well, think of it in two pieces. So you're first going to move along the vector A. So the action of A takes you to here. And then the action of B takes you from where A took you to this point. And so A plus B is just like the combined action, where you started to where you ended, if you do both A and B together. Okay, and you wind up with this diagonal that we have here. Okay, so you can always think of vector addition that way, just doing one vector first, the A, and then doing the other vector and just asking yourself, where did I start and where did I end? That's going to give you the sum vector that you're talking about.